Hello, my name's Julian Edgar and I'm the author of a whole bunch of books on car modification, modifying the aerodynamics of your road car, setting up a home car workshop, optimizing car performance modifications and others as well. What I want to do in today's video is talk about designing rubber mounts to suppress vibration that would otherwise be transmitted to your car's body. Think of mounting a fuel pump. Think of mounting a pump that runs a water injection system or an intercooler water spray or anything like that. They're often very noisy, and when they're mounted to the car body, all that noise gets transmitted to the body that shakes as well, and it can become really, really annoying. So how do you design a rubber mount to best suppress vibration? Now, this is a bit more complex than many of the videos I do. There is a little bit of maths in it. It's pretty straightforward maths. There's a few graphs and things of that sort. But once you get your head around it, you'll be amazed at how much more effective rubber mounts are that you actually use in a system, because now you'll actually know what you're doing with them rather than just picking random rubber mounts and putting them in. So what sort of rubber mounts am I talking about? Well, these are often called cotton reel mounts. These are male ones with a threaded spigot out each side. Here are some female versions of those cotton reel mounts. Here are some different mounts where you can see there's room for the rubber to deflect. And here are some different mounts again. And these are for larger machinery. But how do you know what to pick? How do you know what's going to work? Well, there are two ideas that I want you to learn about. Both of them relate to frequency, and frequency is the number of vibrations, the number of movements that are happening per second. So if I said we have a frequency of 50, and then I said it was 50 hertz, it would be 50 vibrations per second. 100 hertz, 100 vibrations per second, and so on. Now, there are two lots of frequencies that we need to be aware of. The first one is what is called the forcing frequency. That's the frequency of vibration or whatever is producing the vibration. The frequency of vibration of the pump, for example. How many vibrations per second are coming out of that device? It might be 50, it might be 100, it might be 200, but we need to know, and I'll show you how you can actually work that out in a minute. Now, let's imagine that pump mounted on the rubber mounts. If we shake that system, even with the pump turned off, it'll vibrate slightly. It'll vibrate on the mounts. What is the natural frequency of the pump sitting on the mounts? Okay, the natural frequency of that system. So we have two different ideas. One is the forcing frequency of the pump, the vibration it's actually emanating, and the other one is the natural frequency of the pump sitting on the mounts. What natural frequency, what does it like vibrating at? Now, I don't expect you to immediately go, aha, I understand all that. I'm going to give you some examples. So let's take a look firstly at forcing frequency. So here's a little pump that I use in intercooler water sprays. And it's a very unusual pump in that it is an AC pump. It runs off mains power. So in a car application, I use a little inverter, and that turns it into, here in Australia, 240 volts, 50 hertz. AC power. If you did the same in the US, you'd probably use a pump that's suitable for 60 hertz, 120 volts. Now, this pump works by having a little spindle inside that goes back and forth, a little piston goes back and forth at the speed of the AC frequency. So we know this pump vibrates at 50 hertz. So what is the forcing frequency? The pump is vibrating at 50 times a second. Okay, it's an unusual pump though, isn't it? What about this fuel pump? Now, I did some research. Fuel pumps spin between 5,000 and 7,000 revs per minute. So if we divide that by 60, we'll get 83 to 116 rotations per second. And if we assume there's one vibration per second, then we're talking about a frequency of about 83 to 116 hertz. Let's just call it 100 hertz. So we're talking about double the forcing frequency of that other pump. Now you can see, knowing the forcing frequency becomes rather important. This one's twice the vibration speed of the pump that we looked at a moment ago. Now, what do we do with that data? We just put it in our heads at this stage. We know the forcing frequency, we jot it down on a piece of paper or put it in our memories, and we'll come back to that in a minute. Now, what about the natural frequency of the item, like a pump, when it's mounted on the rubber mount? Now, here's a mount, a vibration suppressing mount, and I've picked it because you can see it uses coil springs as well as those rubber pads. Now, if we put a big piece of heavy machinery on top of this mount, we know those springs would compress. Okay, so it would be sitting down on those springs, just the same as if you put it on a rubber mount, it would compress the rubber. Now, we'll leave the pump switched off and we'll just hit it gently with a hammer. That'll make the whole system start to shake, and it'll be the pump shaking on top of the mount. Now, what is the frequency at which that system wants to shake? Okay, that is called the natural frequency of the system. So we have the forcing frequency, which is the frequency coming out of the pump of this vibration, and then when we put the pump on top of this mount, leave the pump switched off, and then we give it a shake, what shaking frequency does it naturally want to have? This is the natural frequency of the system. Now, you might say, well, gosh, that's all a bit complicated. How do I work out what this natural frequency is? How do I know what it wants to shake at? Well, there's a really easy way, and you use a graph. What you do is you measure how much the mount compresses when you put the weight of the pump on top. Now let's say it compresses by 5 millimeters, this pretty big mount. How do we work out from that what the natural frequency is? We look at the graph. That 5 millimeter of compression is called the static, I nearly said natural, the static deflection. So what's the static deflection? 5 millimeters, we said. Here's a nice graph, static deflection millimeters. 5, we go up to here, we go across, and the natural frequency is about 7 hertz. So that system would shake 7 times a second if we got it moving by hitting it with our hand, for example. What if the static deflection was only 1 millimeter? Remember, a lot of rubber mounts have very, very small static deflection, like a millimeter. Well, in that case, the natural frequency of that system is about 18 hertz. So it makes a big difference. Now, how do we relate those ideas together? Why are they related? How do they affect one another? To get best vibration reduction, the ratio of the forcing frequency to the natural frequency has to be 3 or greater. In other words, the natural frequency of your mount, of your system, has to be 1/3 of the forcing frequency of the item. Let's take a look using the examples that we've already been looking at. We saw this pump. It had a forcing frequency of 50 hertz because that's how fast the little piston was going back and forth inside the pump. 50 divided by 3 is 17. Therefore, the natural frequency of the mounted system needs to be 17 hertz or less. So what static deflection is that? We go up here to 17 hertz, we go across, the static deflection has to be at least 1 millimeter. Now that's a very small pump. To put it on mounts and have those mounts sink by 1 millimeter needs either very, very soft mounts, or those mounts have to be arranged and so the thing can droop that much. Okay, if you just had 2 mounts underneath that pump, I doubt if that'd even compress 1/10 of a millimeter. It's a very lightweight little pump. So let's look at the next one. The forcing frequency of this particular fuel pump was, we said, about 100 hertz. Now, if we want to get best vibration reduction, we want to divide that by 3. 100 divided by 3 is 33 in round figures. The natural frequency of the rubber mounted system therefore needs to be 33 hertz or lower. 33 up to here. Okay, we can have about 0.4 millimeters deflection and it will work fine. Okay, we only need 0.4 millimeters of deflection, but you can measure that. You can measure that with a set of vernier calipers. Put your pump on the mounts, put the mounts, hold the assembly above the bench, measure the lengths of the mount, put the assembly on the bench, see how much those mounts compress, what the static deflection is, just with a pair of vernier calipers. And as we said, it has to be about 0.3 or 0.4 millimeters. If it's 0.1, you've got big issues. So if we know the forcing frequency, which we can often work out, and if we can measure the static deflection of the mounts, which we definitely can do when the device is placed on them, then we can see how effective the vibration reduction is going to be. Now, I just put in two extra diagrams here. It's a pretty basic diagram. The red block is obviously the pump or whatever we're talking about, and here are the mounts. Now, most people automatically want to put the item directly on top of the mounts, and rubber in compression is very, very stiff. It compresses very, very little in compression, and that's often not the best way, therefore, of doing the mounts. If we put the mounts like this, you can see that the rubber is compressed slightly as that moves downwards, but you can also see the rubber is in shear. It's trying to slide past itself, and rubber in shear works much, much better as a spring than if it's only in compression. So you can see here the static deflection would be a lot higher than the previous diagram. Okay, that one, the static compression, I'll just make it up, might be 1 millimetre. That one, with the same mounts, the static compression might be 5 millimetres. And so you've really got to start thinking about how you use your rubber mounts in order to get adequate static deflection. Either the mounts being much, much softer than most people are using, or they're mounted in a way that gives greater droop, greater static deflection. And here's an example of that pump. Here's the intercooler water spray pump, the 50 hertz forcing frequency, and I don't know if you can see from that angle, but I've used these normal cotton reel rubber mounts, but I've put it and so that the mounts are not underneath the pump, they're to one side of the pump, and so it's like that. The pump is bending the mounts downwards, and so the static deflection is much, much greater. And with this particular pump connected to the bodywork of the car, as you can see there, it was vastly quieter with the mounts organised in that way, because the static deflection was so much higher than if you had the mounts directly underneath the pump. And here's something to keep in mind. If your forcing frequency, the frequency coming out of the pump or whatever the device is the same as the natural frequency of the mount and the pump on the mount, then the vibration is actually amplified. It gets worse, all right? Because think about it, the vibration coming out of your device is at exactly the same vibration level, exactly the same frequency as the system wants to shake anyway. And so they amplify. So I think a lot of people using rubber mounts who actually haven't trialed or thought about some of these issues are actually increasing vibration coming out of pumps and similar devices rather than actually insulating the car from them. So what's the forcing frequency? What is the natural frequency? You want the forcing frequency to be at least 3 times the natural frequency of the system, and in the real world that typically means you need a lot more static deflection than you first thought you needed. Books are called Modifying the Aerodynamics of Your Road Car, Setting Up a Home Car Workshop, Optimising Car Performance Modifications. Lots of hints and tips and tricks in each of those books. Thank you.